So in today's video, although this course is mostly about analysis of electrical machine, but uh, today I am going to discuss in a very short manner that uh, as of now we are discussing only slip ring induction motor, sorry, squirrel cage induction motor, and we have not yet considered wound rotor or slip ring induction motor, or means whatever theory we have discussed as of now is equally applicable to wound rotor and slip ring, or merely suitable for slip or sorry, whatever theory we have discussed is applicable to squirrel cage and slip ring or squirrel cage motor cheaply, because many motors what we see is that most of the induction motor, see, every motor has find its own application, and induction motor is means widely used, because this wide use of this means almost all the spectrums it find its application, at least 80% of cases where we need something to drive, some electrical machine to drive a mechanical load, we think for induction motor. And when it is induction motor, between these two, your squirrel cage and slip ring, the squirrel cage is preferred. Why? Because it is rugged construction wise, almost maintenance free, no movable electrical contact. So why this one is very important feature of this squirrel cage induction machine is that if you use brush slip ring or brush commutator, whatever you do, you have, if you have any movable electrical contact point, then at that contact point there will be a spark, and that will limit your, first of all, that movable electrical contact point will be subject to wear and tear, and it means it invites additional maintenance cost, periodical maintenance, because you have to replace the brush periodically, otherwise you cannot keep it in that form. However, in if there is no such movable contact and every power transfer takes place through induction, then you do not need to go for that kind of periodical replacement. In case of transformer, if we consider the main like your main maintenance cost involves after a certain time we need to replace the transformer oil, because sometimes it becomes if you consider the electrical property of a transformer oil, then it becomes inferior, so we need to replace it. But if we consider that induction machine, there is no such oil also present, so it is almost free of maintenance as long as we are considering squirrel cage induction machine. However, in squirrel cage induction machine there are certain drawbacks, and what are those drawbacks? What I discussed in my circle diagram lecture, that if you want a wide like the stable operating region is between 0 means slip is equal to 0 to slip is equal to the value of slip for which maximum torque occurs. Although the magnitude of maximum torque is independent of your rotor resistance, but the slip at which maximum torque occurs, that depends on rotor resistance. And if we use a higher value of rotor resistance, we can have that slip occurs, means slip at which we get maximum torque. Let us call it SMT. SMT will occur or will appear at a higher slip range, or we can have a wide range of speed variation. But that wide range of speed variation able means we can achieve by means of by paying the cost of uh, uh, means additional rotor heating. That is not desirable, no way desirable. So the squirrel cage, the advantageous part is rugged, maintenance free, no electrical contact, therefore no such spark, no warranty or no periodic maintenance requirement. And also the important point is that if it is spark free, then you can place it somewhere where there is a chance that combustible gases may be present, like in mining application. If you want to drive some load, you cannot go with DC motor, because in DC motor there will be brushes and brush point contacts. So there means if those combustible gases like methane or argon, they come means methane, ethane, all this comes in the proximity of your machine, and inside that machine there is a continuous sparking takes place during operation. There is a chance that you end up using means end up having a catastrophic accident. So here this is very important point to note, that all these are the advantageous side of squirrel cage machine, but we know that nothing comes to us free of cost. Whenever we are looking for some advantage, we need to pay a price, and the price in case of squirrel cage induction motor is price in terms of disadvantage. And what is the disadvantage? Disadvantage is the squirrel cage disadvantage is that narrow now you may argue that some narrow speed variation is good, because that implies almost machine operates almost in constant speed region like our DC shunt machine. So if there are DC shunt motor, then why should we be bothered at all with this narrow speed variation? But the answer is that it is not only about torque or output power. Sometimes you need, for your own requirement, you need your machine to be means machine should be operated at a low speed without any changing in your supply side. So that is difficult with your this means squirrel cage machine. Another problem of this squirrel cage induction machine is that low starting torque. Why? Because if we consider the starting torque expression, you will see that during starting S is equal to 1, and the starting torque is directly proportional to our R2 dash. However, there is an upper limit of increasing our rotor resistance. If we go to that diagram, we can easily figure it out. Like here you can see that once R2 is equal to X2, that is the critical value of rotor resistance, beyond which if we increase, then there will be no further increase of our starting torque, because maximum torque is R2 is equal to X2, and if you go beneath it, then your maximum torque will decrease. How? Let me show you intuitively. That you can see from this diagram that if we keep on increasing R2, when R2 is equal to X2, maximum torque comes here at slip is equal to 1. That means that is the maximum value of torque is you are getting during start. Now if you further do this R2C, R2 is equal to 2x2, then you are actually not getting the maximum torque in this range. You will get it somewhere here when it is greater than 1. And what is that range? That range is known as braking. Anyway, in this context, let me show you one more diagram that will help you to understand one thing. Yes, we have our diagram with us. Now see that what we are having here is, in this diagram you can see that the slip range S is equal to 0 to S is equal to 1. This is the range of your starting torque, right? This is your stable operating region, right? This is your unstable operating region, but your system still operates in motoring mode. At S is equal to 1, it implies your motor is at standstill condition. Now the question is that what S greater than 1 implies. How can we get S greater than 1? Let us consider a situation when for braking condition beyond S is equal to 1, it is your NS and NR. This region is known as braking region. So this in this braking region, the value of slip is 2 minus S. How we are getting this slip value? Because this region represent your rotor is rotating in, say rotor is rotating in clockwise direction, and your stator MMF is rotating in counterclockwise direction. So the slip what you will get here is what? Slip S will be something because slip is always the relative speed between stator and rotor. So now as the rotor is rotating in opposite direction, relative speed will be added up, like the passengers of two opposite going trains, one is running at a speed of 50 kilometer per hour, another one is running at a 30 kilometer per hour. So once this 30 kilometer per hour will perceive this 50 kilometer per hour is like as if the 50 kilometer per hour is traveling at a speed of 80 kilometer per hour, because the 30 kilometer per hour passenger who is sitting in a train that is running in opposite direction. So here if we apply the same analogy, we will get here the slip value will be So this is our, we can popularly known as backward slip. Backward slip is 2 minus SF. And what is SF? How we are getting this one? It is very easy to show that we do it like NS plus, here we consider as if one MMF is rotating in the direction of rotor, and means we consider two virtual MMF. One is produced by stator, one is rotating in the direction of rotor, another one is rotating in the direction of this stator MMF. And as they are opposite in direction, they cancel out each other. This plus NS minus NS. Again it divided by NS. So what you will have here in this first two term will give you what? The first two terms will give you 2NS by NS, and the second term will give you minus NS. Sorry, it was plus. So that will be 2 minus S. This S is measured with respect to stator rotating at the same speed but in opposite direction. So for an example, you are having a 4-pole machine. So what is the speed of that 4-pole machine, synchronous machine with 50 Hz supply? It is 1500 RPM. Say your stator MMF is counterclockwise. Now consider your rotor is rotating at a speed of 300 RPM clockwise. Then what would be the value of slip? The value of slip will be 2 minus 1500 minus 300 by 1500, that is 2 minus, perhaps this will give you 0.8. So your slip will be 1.2. Now see, in this region that our machine is in braking mode. You can see now in this braking mode, what if we exceed this value, that is the terminal value, that is our, if we make R2 greater than X2, then what would happen? That in this motoring mode we will not get it. We will get a curve like this. So our maximum torque occurs beneath our motoring region. This region is, if you see the curve that I have drawn, it is clearly this curve is not in our, the maximum torque we are not getting in our motoring region. So the point here of stating all this is to make you understand that we should not increase our rotor resistance out of bound, right? Rotor resistance, do note this point. If in any interview you means if your interviewer asks what is the term means critical value of R2, because rotor resistance is proportional to stator starting torque. So what is the critical value of R2? The critical value of R2 is X2, beyond which maximum torque point is not realizable in motoring region. Now, so Okay, and obviously you cannot have higher value of R2 for squirrel cage induction machine because it will cause overheating of the machine. Now think about your other hand. What is the other drawback? That is its high starting current. Why it draws high starting current? The answer lies in this series circuit itself, that at start your S is equal to 1, and if your S is equal to 1, your output power becomes 0. That means this is almost a short circuit. So at start this is a short circuit. So basically at start, if you go for normal starting, you are going to apply full voltage on a short circuited, secondary short circuited transformer. So you can imagine the amount of current that would be drawn by the transformer. Only difference between the transformer and this machine is that transformer cannot change its secondary side resistance, while the motor will start running, and as soon as it starts running, its slip value changes, slip value drops from 1 and its slip value gradually goes to 0, and thereby you will have a gradually increasing resistance effect present there in your rotor side and or means in your secondary side, and that reduces the current requirement. Okay, so I have taken this card from book of MG. Here you can see that this is the standstill condition, and this is our means this is, don't get confused this one with your NS and NR. It is like here it is your NR is equal to 0, and here NS is equal to NR, right? Now NS remains constant throughout the operation if you do not change the supply or the power factor. So it is clear, you can see that this is the value of current. If there is two set of diagram is given, one is for star connected stator and another one is for delta connected stator. So you can see for delta connected stator, the value of current is so high, and even for star connected stator it is so high, and gradually it is means reducing to limit. So see, for star connected stator also, in terms of here you can see that for star connected stator it is how much, it is in the range of, this is current scale, right? So this is 100 for your current scale. See, for star connected stator, this is the value is greater than, means almost 170% of our rated current. And also this diagram indicates a very interesting fact that until you are in star connected stator, you sleep reach something S is equal to 0.15 means 15% means 0.15, above which you are having current that is greater than this value. So clearly it indicates that your full load current is somewhere you are getting full load current at S is equal to 0.5. Interestingly, you can see that around that point you are getting the point of maximum torque also. Right. Now maximum torque you are getting at a current that is slightly higher than your rated current, and the answer even with that approximate circle diagram is obvious, because rated current when your ISC or I2 dash is 100% means sorry pardon me, that rated current you are getting when your that means the total current is 100%, but maximum torque can be means you can get maximum torque if you somehow allow a flow of current that is higher than the rated current. So there is a chance that you may get it. Another explanation is that obviously you don't want your machine the normal current. This is also something that is specified by the manufacturer to this 100%. Who determines this 100%? Even in case of DC motor, I often ask you a question that who decides this base speed? So that and also last week one student asked me that for synchronous machine power circle, who determines the radius of the circle? In all the cases, it is the safety of the winding, the means the amount of current that winding can carry, that determines the our means current limit. So maximum torque you will get somewhere near when your current is 100%, but otherwise it is that. And for delta, obviously the current will be √3 times of star, and you can see this reflection of √3 times for every value of current. It is getting multiplied by a factor of that 1.732. You can figure it the value of √3, and gradually you are getting a higher value of torque. So this is also reveals an interesting fact that in short we can say that star connection, low starting current, or better to write comparatively low starting current, delta higher operating torque. So if we can have a mechanism that allow us to shift between lower torque and means lower starting current and higher starting torque, like what would happen if we allow our machine to start in star mode and then we switch to delta. So of course you may raise a question that sir, in that case what about, because delta it clearly indicates that current is flowing, a high value of current is flowing, but do note that this is line current, not the phase current. Your phase current remains same, but only change here is that phase current, line current has become the phase current in case of star, and that is why it has a limitation in terms of current carrying. But in case of delta, your phase current still remains same as star line current, but the line current of delta is root 3 times of uh, star line current. So here what would happen if you can you start in star, and then when your machine build up speed, you allow it to switch it to delta. So your torque in that case will be something like this. Not this type of smooth switching, means switching is not always so smooth, but more or less this gives you an idea. Now you may argue that with star you are having a poor starting torque compared to delta. But what I want to mention that in case of machine that employs squirrel cage induction machine, it is means we generally try to reduce, or means try to apply minimum amount of load during start. So once we can reduce this amount of load, then what would happen? This much torque, why do you need some starting torque? Just make sure that your motor runs. Even this much torque is sufficient to overcome the no load friction and other retarding torque that is acting on the machine. So you can start in star, and once your machine start building speeds, you switch to delta. Then what is the essence of doing so is that by doing it you can somehow reduce the line current to a considerable extent, right? Means your starting line current remain this, and then when you are means you may sorry you may allow this shift to be taken here also. And obviously your machine, if you see that this entire region is your unstable region, so no operating point you can find here. Even if your torque requirement is this much, what would happen? Your machine will execute a transition and it will settle down here. And for this you can see the value of current. This is not a very huge amount of current, because for that your phase current will be this much. So this gives you some idea about that what about the current and power during start. Let us try to discuss one more diagram. Consider this diagram. Here what we are doing is that we are plotting all these as a factor of our output power. Here we are considering output power as independent parameter. The logic behind this is that output power is something that is governed by our external load demand. So it is considered, and for that this is the rated load. Clearly rated load is less than the maximum torque that you can have here. Now see, for given output you will have different value of your speed, torque and all other things. What is the relation? Now see, another interesting thing, you can see that speed and torque, if you obtain their product, you will see that they are going to give you something like uh, they are quite means for stable operating region, they are giving you a torque, sorry, a power that is almost means for a particular point it remains constant. Means for that point, if you try to deviate, either your speed will reduce or your torque will reduce. Means uh, what I discussed in my circle diagram lecture, for stable operation, you can't have both your speed and torque increasing out of bound. Now for power factor, it is interesting to note that power factor, if you put small load, this side indicates what? This indicates a small load in this region. You can see your power factor is very small, but as we grow, means going to increase our load value, we are getting a good amount of power factor. So at rated load, the value of power factor is around 90% of its full load. Means 90%, means your cos theta will be 0.9. However, you can see that when we will reach to maximum torque, um, then our power will reduce. Here there is a means problem in this diagram is that they have made a mistake with speed and torque. This is our speed curve and this one is our torque curve. Okay, now this is what is happening here about primary current. Primary current, you can see that when load is small, then primary current, obviously for no load also you cannot go beneath this value, and this value indicates this much current indicates what? This much means like even your load is zero, still you are having some current that indicates that your this current represent your magnetizing current and the current required to overcome your no load losses, right? Now that okay, so another thing here is that power factor. Interestingly, you can see that primary current here, this primary current is maximum for your maximum output, that is quite obvious. Now for each and every curve you will see that there is a portion of dotted line, like for this solid torque line. Let me highlight them, otherwise you will get confused. This is our torque line, this is the stable torque operating region, this dash torque line indicates unstable operating region. Now what about our speed? This is our speed for normal motoring region, this is the speed shown by solid line. Now what about our power factor? You can see that this is the stable region of power factor. Then what is the implication of this dashed line for power factor diagram? when we can get this kind of power factor. This actually indicates that we know, see, for every output you are having two value of sleep, and corresponding to this two value of sleep, say you need this much load, so you can operate here and here. So this, for this unstable operating region, you are getting this dashed line of power factor. Similarly, for primary current, you are having this stable region, and the other region is for unstable region. However, it is interesting to note that in unstable region, your current value is very, very high. That is also something interesting to note. Somebody is calling me, just a minute. Now another thing is that efficiency you can also see that we are having a stable region and unstable region. Here is that this is the stable region and unstable region. Clearly, this is the beauty of any physical system. They abide by the laws of nature, and nature always want you to operate, or means to extract maximum benefit from your system. So that is why you can see that efficiency, uh, for poor efficiency falls in unstable operating region. And it happens every time. You cannot help it. For a given machine, if you have two regions, stable and unstable, efficiency always better for your stable region. And the reason is quite obvious, because for efficiency to be having efficiency, higher value of efficiency, you need to reduce the amount of energy in, means there should not be much difference between your output and input. If input minus output is quite high, quite large, then you will have a poor value of efficiency. And if input minus output is high, then what it implies? That means there is a considerable part of your energy is either stored inside the system, or it is going to means dissipate. This it is your system is not able to transfer it from input port to output port. That means this energy somehow is being dissipated through your system, through your means transferring, means if I consider machine as a transferring mechanism, it is means dissipated, transferring through your system. So it is quite obvious that this makes your system, through system, if it dissipates, there is a chance that system get when the systems, that region must not be a stable region. Once your system is like what it receives, it delivers without storing anything, then that is the case of best stable system, like a copper wire. It will means what, as a copper wire, if you consider only a copper conductor as a system, it is always stable. Whatever you will give, it will means deliver. When it will become unstable, see the beauty that when your resistance value of that copper wire R, it is somewhat that I square R is very high, and it crosses that copper wire melting point, and that happens in fuse wire also. So that copper wire at that time starts behaving like an unstable system. So until unless your copper wire starts dissipating enormous energy, it will always be in stable region, because if you consider its efficiency as a term, means current conducting wire, it's very high in normal region. Now, with all this, okay, another few important point here we must not forget to discuss is that how, as I have mentioned, this is not a design course, but I would like to discuss it here because with this knowledge you will find them helpful while addressing your get questions and other question paper, that how different factors of machine, different parameters of machine influence your means performance. Now let me write that rotor resistance. I hope that part is clear. Now let us come to the air gap. What about what do you think about air gap? Should we keep a high air gap? Now, a large air gap means high value of air gap between your lies what? Better cooling, but and less mechanical loss, but what would happen? It will affect your power factor, and poor power factor means what? For same load, your machine will draw more current, and even during magnetization, so current this is due to large air gap and small air gap. All these con will become pro and pros will become con for small air gap. Like small air gap, you will have means cooling part, means cooling of machine will become a challenge, and somewhat mechanical loss means air will friction will increase, and higher value, however, that will cause comparatively lower starting current, and that leakage, magnetic leakage will be small if you make a comparatively small air gap. Now, depending on your machine requirement, we need to decide. However, what do you think that, okay, and needless to say that if you means operate at a poor power factor, that will also going to affect your that is going to affect your efficiency. But what about the torque? Do you think if we increase the air gap, then the torque will increase, or if we reduce the air gap, then we can have a higher torque getting from our machine. Or in other way, the torque remain unchanged irrespective of your machine air gap. Now, like if you consider that if you have something like what to say, that if you reduce the air gap, then your machine torque profile will be enhanced. How? You will answer me if you are means holding your nerve and still watching this video. You please answer me, because this is a question that is going to come in your semester exam, that how torque profile will be means will be affected with the variation of air gap. Now another thing is that it's like our yes. So okay, now let us come to different type of stator slot. What are the stator slots we can have? We can have three different type of stator slots. One is open, here you have this conductor. This is an example of open slot. Then you have this is a semi-closed slot. Another slot is this is closed slot. Now, what is the advantage of having open slot? That closed slot, if you compare, having the highest value of leakage. And open slot is having minimum value of leakage reactance. Now, if your leakage reactance is small, then what it implies? Smaller leakage reactance implies high starting torque and high pull out torque. However, the problem with this small leakage reactance is that a dangerously high value of starting current. I am using reading to make it understandable that small leakage reactance implies high starting current. It is quite obvious because leakage reactance appears in series. So if you reduce the value of this leakage reactance, then it is going to cause a very high flow of starting current through your machine. And also another means small leakage reactance also good in terms of high power factor, offering high power factor. It's all these are quite obvious. Now this is extreme one, like open is having the minimal value of leakage and closed slot is having the maximum value of leakage. So that is why we go for semi-closed in most of the time, where your conductors are partially closed, not fully open, not fully closed, and we get the average of all its benefits. Like we obtain a trade-off between high starting current and high starting torque. We obtain a trade-off between high power factor and our like high means like high starting current. So this is the essence of machine design, that you must understand that you cannot be eccentric and go to a single direction, like a means single direction is not possible in machine design. You must be running an optimization algorithm to do several trade-offs between several factors, and that will give you the particular idea of your machine structure. Now, what about rotor? This is all about when we are discussing as long as it is stator slots. Now, what about rotor slots? Now, starting torque is directly proportional to rotor resistance, and rotor resistance must be high, but for that reason, but higher rotor resistance is means cooling will be affected, and also your efficiency will be poor. All this will be of concern. And the major problem with squirrel cage induction machine is that your rotor circuit is not accessible to the outside operator. Unlike slip ring induction motor, slip ring, 3 slip rings are there and you have a provision to alter the electrical circuit of the rotor. But in case of your squirrel cage induction motor, rotor is intact and there is no electrical connection is possible between rotor and stator, means rotor and the outside operator. So how we can do it? The answer is that to make squirrel cage machine performance better, what we do is that we go for deep bar rotor. What is the deep bar rotor? In deep bar rotor, the groove depth is quite means and than that normal groove depth in terms of means for suppose this is your normal groove depth. If we consider it D, here it is D dash. What is your rotor surface? Rotor surface is like this. Just a minute, let me insert one image. These are rotor means slot. Now deep bar slot means what? Deep bar slot means these slots are like this much. So what advantage that deep bar slot offer? If we draw the rotor part, rotor 1 deep slot, that what we will have here is that we can have three different types of deep bar. One is this is known as parallel side bar deep bar. Another one is trapezoidal, and the third one is T bar. Now what they do is that at starting S is equal to 1, so rotor frequency is equal to F2 is equal to F, because F2 is equal to SF, so F2 is equal to F at starting. Now this deep bar rotor frequency is equal to the supply frequency, then the bottom part of the bar offers more impedance to the current than that of the top part. Well, before I proceed, one thing I just want to mention, this T bar is having mechanical advantage because you can understand the way it is holding the conductors. Conductors is like filled here. Now you can see that a part of conductors is solidly means embarked inside this group. So it gives us most mechanical strength. So this is mechanically advantageous design. Anyway, so let us go to this one, that when we are dealing with this F2 is equal to SF, so at starting the rotor frequency is equal to supply frequency, and the bottom part of the bar that offers more impedance to the current than the top part. Why? Because in the bottom part means like this is actually this is all due to your skin effect, is that means when your machine is trying to start, then what your this lower part of your just a minute, let me see whether any animation is available or not. Unfortunately, I didn't get any suitable such means your animation, but anyway, what we know that skin effect is higher for high value of frequency, and in deep bar what happens that the leakage flux linked with the bottom part. Let me try to do it to make you understand. Suppose if we cut it in two segment, then the conductor that lies in this region, what is happening here, the conductor that lies in this region, here this white shaped region, and the conductor, obviously there is no such barrier is there that demarcates to a conductor, but what we are having here is that these white color conductors are having much more is associated with more leakage flux. Therefore, the at starting, when the supply frequency is quite high, the bottom part of the bar, this white one, this is having a higher value of impedance. So what will happen? This bar, total bar appear to current, like current is water, and you are having two pipes. One is this white color pipe, another one is green color pipe, and you are having white color pipe diameter is this much and green color pipe diameter is this much. So which one the water will prefer? Obviously water will prefer this one. However, as your means machine build up speed, S will become small and S will tends to 0, and then what you will have, this leakage will reduce in the lower part, and you will have more or less same diameter for your rotor. So using skin effect, we can using this deep bar rotor, and also another variation is there, double cage rotor. Both are using the same thing, that lower part offers high frequency, means higher impedance, and thereby we can have this kind of advantage. In double cage rotor, sometimes what we do, we intentionally use high resistance conductor here. So basically during start, what happens that you are having two, it is like you are having one wider means two small pipe at start, and when it is in run, once pipe diameter is getting enlarged, and your majority of water can flow through this large pipe. So this is something of double bar double sorry it is double cage, or it is also known as Boucherot. There you will have two different cages, like this will look like the rotor slot looks like this, or this kind of deep bar rotor. Obviously all these sounds fascinating, but it also takes a toll in terms of the higher designing and manufacturing cost, because this kind of design obviously needs more effort and more involves more manufacturing costs. So all this doing this trade-off, you can get good and means uh, good performance squirrel cage induction motor at an affordable price.